Hello and welcome. In this video, we will explore the application of vectors to describe lines in both 2 and 3 dimensions. This is a fundamental topic in the IB Mathematics Analysis and Approaches higher level curriculum. By the end of this session, you will be able to: first, write the vector, parametric, and Cartesian equations of a line. Second, determine the angle between two lines. And third, solve problems involving parallel and perpendicular lines. Let's begin by understanding how to define a line using vectors. In both 2 and 3 dimensions, we can uniquely define a line if we know two things: a fixed point on the line and the direction in which the line extends. Let's visualize this. Suppose we have a fixed point A with a position vector, which we'll call A. This vector starts at the origin and ends at point A. Now, let's say the line is parallel to a direction vector, which we'll call B. This vector B tells us the orientation of the line. Our goal is to find the position vector, R, of any arbitrary point R on this line. By vector addition, the vector R is the sum of the vector A and the vector from A to R. So we can write this as R equals A plus the vector AR. Since the vector AR lies on the line, it must be parallel to our direction vector, B. This means that AR is a scalar multiple of B. We can write AR equals lambda times B, where lambda is a scalar parameter that can take any real value. Now we can substitute this back into our equation for R. This gives us the vector equation of the line. R equals A plus lambda B. This equation generates every point on the line as lambda varies. Let's recap. The vector equation of a line is R equals A plus lambda B, where A is the position vector of a known point on the line, B is the direction vector of the line, and lambda is a scalar parameter. Now that we have the vector equation, let's see how we can express it in other forms. We'll start with parametric equations. Let's consider a line in 3 dimensions. Suppose our arbitrary point R has coordinates x, y, z, our fixed point A has coordinates a1, a2, a3, and our direction vector B has components b1, b2, b3. We can write the vector equation using these components. The position vector R is the column vector x, y, z, the position vector A is a1, a2, a3, and the direction vector B is b1, b2, b3. To get the parametric equations, we simply equate the corresponding components on both sides of this vector equation. This gives us 3 separate equations: x equals a1 plus lambda b1, y equals a2 plus lambda b2, and z equals a3 plus lambda b3. These are the parametric equations of the line, with lambda as the parameter. Next, let's derive the Cartesian equation. We can do this by eliminating the parameter lambda from the parametric equations. From the first equation, we can solve for lambda. Lambda equals x minus a1 all over b1. We can do the same for the other 2 equations. Since lambda is the same for all 3, we can set these expressions equal to each other. This gives us the Cartesian equation of the line: x minus a1 over b1 equals y minus a2 over b2 equals z minus a3 over b3. This form is also known as the symmetric form. It's important to note that if any component of the direction vector, say b1, is 0, the Cartesian equation needs to be adjusted. For example, if b1 is 0, the line is parallel to the yz plane, and the equation becomes x equals a1, and y minus a2 over b2 equals z minus a3 over b3. Let's work through an example to solidify these concepts. We'll take a line in space and describe it using all 3 forms. Consider a line that passes through the point 1, minus 2, 3, and has a direction vector of 4i plus 5j minus 6k. First, let's write the vector equation. We need a position vector, A, and a direction vector, B. The position vector, A, is the vector from the origin to our point, which is 1, minus 2, 3. The direction vector, B, is given as 4, 5, minus 6. Plugging these into our formula R equals A plus lambda B, we get the vector equation. The vector, x, y, z, equals the vector 1, minus 2, 3, plus lambda times the vector 4, 5, minus 6. Next, let's find the parametric equations. we equate the components. This gives us x equals 1 plus 4 lambda, y equals minus 2 plus 5 lambda, and z equals 3 minus 6 lambda. These are the parametric equations. Finally, for the Cartesian equation, we eliminate lambda. Solving each parametric equation for lambda, we get lambda equals x minus 1 over 4, lambda equals y plus 2 over 5, and lambda equals z minus 3 over minus 6. Setting these equal gives us the Cartesian equation. X minus 1 over 4 equals y, plus 2 over 5 equals z minus 3 over minus 6. So we have successfully described the same line using 3 different but equivalent forms. A common question is how to find the equation of a line when you are given 2 points on it, instead of a point and a direction vector. Let's find the parametric equations for the line passing through point A with coordinates 2, minus 1, 4, and point B with coordinates minus 1, 0, 2. Remember, to write the equation of a line, we need a point and a direction vector. We have 2 points, so we can choose either one. Let's use point A. So our position vector, A, will be 2 minus 1, 4. Now we need a direction vector. The vector connecting the 2 points, A, B, will lie on the line and can serve as our direction vector. The vector AB is found by subtracting the position vector of A from the position vector of B. This gives us minus 1 minus 2, 0 minus minus 1, 2 minus 4, which simplifies to minus 3, 1, minus 2. Now we have our point and our direction vector. We can write the parametric equations. Using point A and direction vector AB, the parametric equations are x equals 2 minus 3 lambda, y equals minus 1 plus lambda, and z equals 4 minus 2 lambda. It's important to note that this is not the only correct answer. We could have used point B as our fixed point, or we could have used the vector BA as our direction vector. The resulting equations would look different but would describe the exact same line. Now let's shift our focus to the relationship between 2 lines. We'll start by defining the angle between them. The angle between 2 lines is defined as the acute angle between their direction vectors. We use the dot product formula to find this angle. The formula is cosine of theta equals the absolute value of the dot product of B1 and B2 divided by the product of their magnitudes. We use the absolute value to ensure we get the acute angle, which is between 0 and 90 degrees. Let's apply this to an example. Find the angle between the lines L1 and L2 given by their parametric equations. First, we need to identify the direction vectors for each line. For L1, the coefficients of the parameter, t, give us the direction vector B1, which is minus 3, 1. For L2, the coefficients of conem S give us the direction vector B2, which is 2, 3. Now, we can plug these into our formula. The dot product B1 dot B2 is minus 3 times 2 plus 1 times 3, which is minus 6 plus 3, or minus 3. The magnitude of B1 is the square root of minus 3 squared plus 1 squared, which is the square root of 10. The magnitude of B2 is the square root of 2 squared plus 3 squared, which is the square root of 13. So cosine of theta equals the absolute value of minus 3 divided by the square root of 10 times the square root of 13. This simplifies to 3 over the square root of 130. Taking the inverse cosine, we find that theta is approximately 74.7 degrees. This is the acute angle between the 2 lines. The dot product formula also gives us a powerful way to determine if 2 lines are parallel or perpendicular. Consider 2 lines, L1 and L2, with direction vectors B1 and B2. The lines are parallel if their direction vectors are parallel. This means one direction vector is a scalar multiple of the other. So B1 equals k times B2 for some scalar k. The lines are perpendicular if their direction vectors are perpendicular. This occurs when their dot product is 0. So B1 dot B2 equals 0. Let's look at an example involving perpendicular lines. Show that the lines L1 and L2 are perpendicular. First, we extract the direction vectors. The direction vector for L1, B1 is 5 minus 3, 2. The direction vector for L2, B2 is 4, 10, 5. Now we calculate their dot product. B1 dot B2 equals 5 times 4 plus minus 3 times 10 plus 2 times 5. This is 20 minus 30 plus 10, which equals 0. Since the dot product of their direction vectors is 0, the lines L1 and L2 are perpendicular. This confirms our objective. Let's tackle a more complex problem that combines several of these ideas. We'll find the equation of a line that is perpendicular to two other lines. We have two lines, L1 and L2. L1 is given in vector form, and L2 is given by 2 points. We need to find the Cartesian equation of a third line, L3, that is perpendicular to both L1 and L2, and cuts the z-axis at minus 2. Find the equation of L3 in Cartesian form. First, let's find the direction vectors for L1 and L2. The direction vector for L1b1 is given directly as minus 1, 1, 4. For L2, we find the vector connecting the 2 points, which is minus 4, 1, 0. Now, L3 is perpendicular to both L1 and L2. This means its direction vector, B3, must be perpendicular to both B1 and B2. We can find such a vector using the cross product. The cross product of B1 and B2 will give us a vector that is perpendicular to both. Calculating the cross product, we get the vector minus 4, minus 16, 3. This is our direction vector for L3. Next, we need a point on L3. We are told it cuts the z-axis at minus 2. Any point on the z-axis has x and y coordinates of 0. So the point is 0, 0, minus 2. This is our position vector, A, for L3. Now we have a point and a direction vector for L3. We can write its Cartesian equation. Using the formula, we get x minus 0 over minus 4 equals y minus 0 over minus 16 equals z minus minus 2 over 3. This simplifies to x over minus 4 equals y over minus 16 equals z plus 2 over 3. This is the Cartesian equation of L3. Let's conclude with a final, more advanced problem that involves finding the minimum distance from a point to a line. A line has parametric equations x equals 1 plus lambda, y equals 2 minus lambda, and z equals 3 plus lambda. We want to find the point on this line that is closest to the point P with coordinates 1, 1, 2. Let x be any point on the line. Its coordinates are given by the parametric equations. The vector px connects the point P to any point x on the line. The vector px is found by subtracting the coordinates of P from the coordinates of x. This gives us the vector lambda, 1 minus lambda, 1 plus lambda. The distance from P to the line is minimized when the vector px is perpendicular to the line's direction vector. The direction vector of the line, B, is 1 minus 1, 1. For px to be perpendicular to the line, their dot product must be 0. Calculating the dot product, we get lambda times 1, plus 1 minus lambda times minus 1, plus 1 plus lambda times 1. This simplifies to 3 lambda equals 0, which means lambda must be 0. So the minimum distance occurs when the parameter lambda is 0. To find the point on the line, we substitute lambda equals 0 back into the parametric equations. This gives us x equals 1, y equals 2, and z equals 3. The point on the line closest to P is 1, 2, 3. Let's quickly recap what we've covered. We've learned how to represent a line in space using 3 different forms: the vector equation, the parametric equations, and the Cartesian equation. We saw that the vector equation R equals A plus lambda B is the foundation, from which we can derive the parametric and Cartesian forms. We also learned how to find the angle between two lines using the dot product of their direction vectors. The formula cosine of theta equals the absolute value of the dot product of B1 and B2 divided by the product of their magnitudes gives us the acute angle. And we established the conditions for parallel and perpendicular lines. Lines are parallel if their direction vectors are scalar multiples, and they are perpendicular if their dot product is 0. Finally, we saw how to solve more advanced problems, such as finding the equation of a line perpendicular to two others, and finding the point of minimum distance from a point to a line. To help you master these concepts, here are 5 practice questions in the style of the IB exam. Pause the video, work through them, and then resume to see the fully worked solutions. Here are the questions. Take your time to solve them. Welcome back. Let's go through the solutions. Here is the solution to the first question. For part A, the vector equation is r equals the position vector of A, which is 2 minus 1, 3, plus lambda times the direction vector B, which is 4, 1 minus 2. For part B, the xy plane is defined by the equation z equals 0. We set the z component of our vector equation to 0. This gives 3 minus 2 lambda equals 0, so lambda is 3 halves. We substitute lambda equals 3 halves back into the x and y components to find the coordinates of the intersection point, which are 8 minus 1 half, 0. Here is the solution to the second question. To show the lines are perpendicular, we need to show their direction vectors have a dot product of 0. The direction vector for L1, B1 is 2, minus 1, 1. The direction vector for L2, B2 is 1, 3, 1. Now, we calculate their dot product. B1 dot B2 equals 2 times 1, plus minus 1 times 3, plus 1 times 1. This is 2 minus 3 plus 1, which equals 0. Since the dot product is 0, the direction vectors are perpendicular, and therefore the lines L1 and L2 are perpendicular. Here is the solution to the third question. First, we need to find the direction vectors. For L1, we read the denominators of the Cartesian equation, giving B1 equals 2 minus 1, 1. For L2, we read the coefficients of the parameter t, giving B2 equals 1, 2 minus 1. Next, we calculate the dot product and magnitudes. The dot product is minus 1. The magnitude of B1 is the square root of 6, and the magnitude of B2 is also the square root of 6. Using the angle formula, cosine of theta equals the absolute value of minus 1 divided by the square root of 6 times the square root of 6. This simplifies to 1/6. Taking the inverse cosine, we find the acute angle between the lines is approximately 80.4 degrees. Here is the solution to the fourth question. For part A, we need a point and a direction vector. We can use P as our point, so A equals 1, 0, 2. The direction vector B is the vector PQ, which is 2, 4, minus 2. The vector equation is R equals 1, 0, 2, plus lambda times 2, 4, minus 2. For part B, we derive the Cartesian equation from the vector equation. The parametric equations are x equals 1 plus 2 lambda, y equals 4 lambda, and z equals 2 minus 2 lambda. Eliminating lambda gives the Cartesian equation x minus 1 over 2 equals y over 4 equals z minus 2 over minus 2. Finally, here is the solution to the fifth question. We need to find the shortest distance from point R to line L. Let x be a general point on the line. The vector Rx connects R to x. The shortest distance occurs when Rx is perpendicular to the line's direction vector B. The direction vector B is 1, 2, minus 1. We set the dot product of Rx and B to 0. This gives us 6t minus 3 equals 0, so t equals 1/2. Now we find the vector Rx for t equals 1/6. This gives us 7/6 minus 4/6 minus 1/6. The shortest distance is the magnitude of this vector, which is the square root of 66 over 6. That concludes our exploration of lines in 2D and 3D using vectors. We've covered the essential concepts and worked through several examples, including some more challenging problems. Remember, practice is key to mastering these skills. Continue working through problems from your textbook and past papers. Thank you for watching.